Chapter 41, Quantum Mechanics. In this chapter, we're going to study further the principles and applications of quantum mechanics. In a previous chapter, we established the central idea of quantum mechanics, which is the wave-particle duality. In fact, quantum mechanics is often also called wave mechanics because of the wave nature of particles. And when it comes to a wave, we can always use a wave function to describe the wave. For example, a sine wave is different from a wave packet, which is made of a bunch of sine cosine waves. So, can we establish a wave function to describe the behavior of a particle? And if we establish a wave function, what is the equation we can use to solve that wave function? And once we have that wave function, what can we get out of that wave function? Those are things we'll be discussing in this chapter. We'll look at various examples of particles in different potentials with different wave functions. So let's take a closer look at what's called a wave function. I can define a wave function of a particle at a certain location at a certain moment. We try to find an equation which allows us to find this wave function, and then we get this wave function. From there, we will find the properties of this particle, such as where it is, how fast it's moving, what is the value of its momentum, and so on and so forth, if we are able to do that. So the first order of business is for us to find an equation, which is actually a differential equation, which gives us the wave function. Given the wave function, we'll see that we can find everything we can find about this particle. So the wave function really is the most important thing we should get for this particle, and therefore the equation for that wave function is of central importance to quantum mechanics. In fact, the importance of this equation is just the same as Newton's second law for classical physics. And believe it or not, this equation, which we'll be trying to get in the next moment, is related to Newton's second law in the right circumstances. One thing we must keep in mind before we start to try to find this equation is that there is no derivation for this equation which we set to find out. This is in fact analogous to Newton's second law. Can we prove Newton's second law from a higher principle in classical mechanics? Well, the answer is no. We have never done that, in fact. How do we know Newton's second law is right? Because if we set Newton's second law and we calculate the behavior of a particle with Newton's second law and we compare with the experiment, we always find it to be true, right? So that's why we say Newton's second law is right. We're going to do the same thing here. We cannot derive the equation, but we're going to guess it, okay? We're going to put an educated guess as to what this equation should look like. And once we have that equation, we are going to put it to test. We are going to try to solve the properties of a particle with the solution to this equation and compare that with experiment and see what happens. So how do you guess this wave function, the equation for this wave function? Well, the simplest wave function is a function for the simplest behavior of a particle, that is a particle moving freely under the influence of no force. It's what's called a free particle, right? So we're going to take a look at how the wave function for free particle should look like and what kind of equation can we write for this free particle, and then we go from there. So here is the wave equation for a free particle. The wave function for free particle, psi naught, as we saw in a previous chapter. This is what we use for a free particle, the wave equation, e to the I kx minus omega t. That describes a plane wave traveling along the positive x direction. The wave vector is k, which is 2 pi over lambda. Omega is the frequency of this wave. So this is a wave, again, traveling along the positive x direction. We call it psi naught. And you notice we did not quite use sine or cosine, rather we used e to the I. This, you will see in a minute why this is the right choice instead of sine and cosine. And for this free particle, there is no potential energy. The total energy is just equal to its kinetic energy, which is p squared over 2m, assuming the particle does not move at relativistic speed, so we don't have to use relativity. It's just p squared over 2m, that is its kinetic energy. But p equals h bar k, or the x direction. The x component of p is equal to h bar k, assuming it doesn't really move in the y and z direction, okay, for simplicity. So it's h bar squared k squared over 2m. That is the kinetic energy or the total energy of this particle. Now, for this very simple case, we don't really need a wave equation, do we? Because we already have the solution to that equation, right? But what we try to do here is that we try to guess what this equation is, right? And to do so, we take this given case or known case, which is the free particle. We already know the solution. Can we guess what the equation is from the solution in this simple case? So usually it's the other way around, right? Usually we take the equation, we try to solve the equation to get the solution. Here we go backwards. We have the solution, we try to guess what the equation is. Now we know that the total energy of a particle is equal to its kinetic energy plus its potential energy. And here is, suppose it only moves in the x direction, the kinetic energy again is px squared over 2m. The potential energy is u, which can be anything. Now, suppose I apply E equals k plus u to this particle, to this particular case of free particle, by multiplying both sides of E equals k plus u with this wave function of this free particle, e to the I kx minus omega t, then this is what I get, right? Well, in fact, u is equal to 0 in our case, or at least equal to a constant in our case. But let's pretend that, we don't worry about that. We just leave it as is, okay? I want to focus your attention on this term, the kinetic energy term. Right now, what we have here is an equation which is valid for the free particle case. For the free particle, since there is no force, that's what we call it free particle, right? The kinetic energy is a constant. In fact, even the linear momentum in the x direction is a constant because there's no force, no acceleration. But in more complicated cases, there is a force acting on a particle, and as a result, its linear momentum will change in the x direction due to the acceleration given by that force. So P of x itself is not a constant. You cannot simply multiply like that. So is there a way we can turn this into a differential equation which is valid for the most general case when u is not quite equal to 0 or a constant? Well, we can see what we can do for this free particle first, and then we try to generalize it to a general case. For this free particle, look at the solution. The solution is e to the I kx minus omega t. I mean, there is an overall constant here, but I don't really care about that because this, as you can see clearly, is a linear equation, so the constant doesn't really matter. How do I turn this term into a differential operator so that the equation becomes a differential equation? Well, for this particular wave, the wave for a free particle, I know how to do that. Because all I need here is to get px squared over 2m out of this psi naught, right? Psi naught is e to the I kx minus omega t, which is the same as px over h bar and then minus omega t. Okay, minus omega t. Now, what I want is to bring the px squared down from the from this wave function. Is there a way to bring this p down here from a mathematical point of view? Well, if you know calculus, which of course you do, you know what we can do, right? You have an exponential function, right? If you differentiate this exponential function with respect to x, then everything else, this I, this p, this h bar, will all come down, right? So let's do this. Let's try partial x and see what we get. Partial x. Okay? And then if we did that, just like I said, you're going to be able to take that p down, in fact, along with I and h bar. So you got I px over h bar. Okay? And then you have the same wave function, e to the I px over h bar minus omega t. Now, remember, I don't want I px over h bar. I want p. I want just a linear momentum. Okay, so what I'm going to do now is I want to get rid of I and h bar, so I'm going to move h bar over there and move this I down there. So you get h bar here divided by I. 1 over I is negative I. So therefore, I found that negative I h bar partial x, this thing, this differential operator, acting on the wave function of this free particle psi naught, is just equal to px psi naught. And therefore, I know that I can replace px with this differential operator. I replace it with negative I h bar partial x. If you operate this on a free particle, the wave function, you're going to get the same result, whether you multiply by px or you differentiate the wave function with this differential operator. So this is the kinetic energy. I'm sorry, this is the linear momentum. What about the whole kinetic energy? Well, then you need p squared, right? For p squared, you just have to differentiate twice, second derivative, because for every derivative you get a p. You want a p squared, you just do it again. So therefore, the kinetic energy is given by the following. You take this operator, you square it, and divide it by 2m, okay? So you square that, 1 over 2m, and then you negative I h bar partial x. You square that. Now let's work that out. Negative I, you square that, that's negative 1. So it's minus h bar squared over 2m times the second derivative with respect to space. So this operator, this differential operator, acting on psi naught will give you k. So I'm going to write this down here, negative h bar squared over 2m times the second derivative operating on our free wave function would equal to k, the kinetic energy times psi. Okay? Now, what about the total energy? Well, the total energy is related to omega. Because for a photon, the energy is related to its frequency like this. E equals hf, right? And this can be extended according to de Broglie relation beyond a photon. It's valid for any particle. And I can rewrite this as h over 2 pi times 2 pi f. H over 2 pi, as you know, we call it h bar. 2 pi f is just omega, so this is h bar omega. Okay, so that's the total energy. I know there's an omega here, so I need to bring that omega down if I want to find a differential operator which will give me the total energy. So I need to differentiate with respect to what? To time, right? When I do that, omega will come down. So let me differentiate psi naught with respect to time. So that's what I'm going to do, psi naught. And I do that, partial t, okay. And what do I get? Okay, it's negative I omega coming out, negative I omega, times whatever is left, so that's psi naught. Now, this is negative I omega. What I want is h bar times omega. So what I'm going to do is I'm going to turn this negative I into h bar by multiplying both sides by a factor, first of all, by a factor h bar, so minus h bar. And then I don't want that negative I, so I'm going to move it over there. So in the denominator on this side, I have negative I in the denominator, which is the same as just I in the numerator. So therefore, I find another differential operator which will give me the total energy, and that is I h bar partial t, okay? If you operate this on our free particle wave function psi naught, you are going to get energy times psi naught, energy being h bar times omega. So for this free particle, I can take the energy E, replace it with this operator, take the kinetic energy, replace with that operator, and finally, I have this U here, which is just a number, which is just a function of x. I don't want to turn it into an operator because there's just potential energy U. Now, to be strict, none of these expressions I have proven to be true for any arbitrary function U or any arbitrary potential, because I only operate these operators on the free particle for which U is no more than just a constant, okay, which we often define to be 0. So for this free particle, I know that I can write down a differential equation, which is E, instead of E psi naught equals K psi naught. I can write E replacing with negative I with, I h bar partial t, right, as I just did before, psi naught. That equals K I change that to a differential operator negative h bar squared over 2m times the second derivative with respect to x psi naught. This is just as good as E equals k multiplied by psi naught on both sides. But this is only valid for sure for a free particle. Now what if I have a particle that's not quite free? It's got a potential which can both vary as function of space and time. Can I extend this discussion? Well, it turns out at this point I have to take a bold guess. Okay? This is energy equals kinetic energy. If you have a potential energy, then why don't we just add a term, potential energy, and multiply by psi naught? For psi naught, of course, I can do that. In fact, psi naught is often considered as zero U is often considered as zero as long as it doesn't vary. It's just a constant, which I also take as zero. But if it's not a constant, can we still retain this as the differential operator for E and this as a differential operator for the kinetic energy? In other words, can I take this equation and just erase that zero sign here to replace phi as any arbitrary wave function under any arbitrary value or any arbitrary potential? Well, this is again a bold step, and nobody knows whether it's true or not, but let's pretend we can do that. Okay, then I arrive at the following differential equation. I h bar partial psi partial t equals to negative h bar squared over 2m partial psi partial x second derivative plus u psi. I arrive at this, right? This is assuming that the motion occurs only on the x-axis, so there is no y and z dependency. Can we extend this beyond one dimension? Well, that's not that hard to do. For 3 dimensions, t is still t, but this x is now replaced by a combination of x, y, and z, so therefore I have this. Replaced with what? With the gradient squared operator. That's the Laplace operator, which is the sum of these 3 terms. Because there is motion in both x, y, z direction, in all these 3 directions. So there's px, py, pz, not just px. And then I have arrived at a 3-dimensional differential equation. I h bar partial psi partial t equals to the first term, which is now the kinetic energy term, which is now gradient squared, okay, which is this psi, plus u psi. U again can be a function of r and t. This equation, which I guessed out of free particle wave function, is called Schrödinger's equation. It was first proposed by the Austrian physicist Owen Schrödinger in 1926. This equation is the equation we're going to use to find the wave function. Again, we never claimed this to be a rigorous proof, because in jumping from free particle to any situation with an arbitrary potential energy, we never said this jump was guaranteed to be successful. But what we're going to do is we're going to take this and solve the differential equations for examples of U, and to see whether our solution agrees with experiment or not. If it is, then our equation must be right. Okay, this is called the Schrödinger's equation. The Schrödinger's equation has the same position in quantum mechanics as Newton's second law in classical mechanics. It is of central importance in our understanding of the behavior of a particle as a wave. So as you can see, the Schrödinger's equation is fairly complex because it involves both space and time variations. You have to take partial derivatives with respect to space and time. Now, there is, however, an important special case, and that is when the potential function u is only a function of space, r, but it's not a function of time, t, which means we basically have a constant, if non-uniform potential. In classical physics, we know what happens when the potential is only a function of space, not a function of time. Basically, what we have here is conservation of energy, right? Now, if the potential energy change over time, then of course the total energy, which is kinetic plus potential, can also change over time. But if u is not a function of t, can we simplify this equation? Well, let's see what we can do. That's an important special case. We suspect that in our case, we still have the total energy, which is kinetic plus potential equals a constant if u doesn't depend on time. But in quantum mechanics, we know the energy is related to omega, the frequency. So therefore, we suspect that omega might also be a constant. Now, is that true? Can we simplify the Schrödinger's equation in this case? Well, let's see here. The trick we have is to separate the time variable t from the space variable r. In other words, let us assume that psi, which is generally a mixture of space and time, can be written as the product of two functions, two separate functions. This is a wave function which has to do with space. This is the time part of this wave function, a different function which has to do with time only. Now, there is no guarantee that this scheme is going to work, but let's pretend it might work. We plug into the equation. If we can successfully solve this equation, then it works. Otherwise, we just don't worry about it anymore. Okay, so let's plug that in. Right? Let's see what we can do. This is the original Schrödinger's equation, IH bar partial t psi. That's the left-hand side of the original Schrödinger's equation. But psi itself is now divided into these two parts, space part and time part, right? And remember, this differential operator only works on the time part. So I'm going to take the space part, which is psi r, I'm going to take that out along with IH bar, so it's here. What's left is the derivative with respect to phi, the time part of the wave equation, and that is not a partial derivative anymore, just d phi over dt. Again, that's the left-hand side of the Schrödinger's equation. Now the right-hand side is the operator for kinetic energy plus the potential energy term u. Again, I'm going to rewrite this wave function in terms of the product of psi and phi, and this right-hand side, whether it's the kinetic energy term or the potential energy term, remember, potential energy does not depend on time, and the kinetic energy operator never depends on time anyways, so the whole thing has nothing to do with time, this operation, and therefore I'm allowed to take that phi and move it out of the differentiation to this side. What's left is this operator acting only on the space part of the equation, right? So this is the right-hand side. Now let's equate the left-hand side and the right-hand side, and then we arrive at this. I use a different color to highlight the time-dependent part, d phi dt on this side and phi on that side. The rest is dependent on space. So I'm going to do a little bit of a maneuvering. I'm going to move phi and d phi dt together to the left-hand side and move this guy over to the right-hand side. So now I have something equals something else. This side, d phi dt divided by phi, I just move phi over, depends only on time. It's a function of time only, okay? And then I move this term over there, which gives me this. This is a function of space, or r, or x if it's a one-dimensional case. So in general, we say it's a function of r. Now that's interesting. It's a function of t, it is a function of r. Generally, a function varies when its variable changes. So when you change t, in general, this whole expression, which is a function of t, may change, right? And same thing can be said about this side. When r changes, generally, this whole thing changes. But wait a minute. These two sides must be equal to each other for any r and any t. Now suppose I fix r. I look at a special point in space. So r never changes, which means this side never changes, right? Which is a function of r only. And then I look at what happens at this point as time changes. So I stare at that point for a long time. I watch what happens when time progresses. In general, this side should change because it's a function of t, right? But wait a second, r never changed because I'm staring at the same point, and therefore this side never changes. Since this side never changes, that side cannot change either, even as time changes. So what did that tell us? It tells us this thing cannot be a function of t. It's just a constant. Okay? The same argument can be made about this because this is a constant and that is also a constant. So both must be a constant. In fact, they must be equal to the same constant. Right? They must be equal to the same constant. And let's call that constant c. Let's call that constant c. So what is c equal to? Well, let's equate this with C. I'm going to move the denominator IH bar phi to that side, so I get IH bar phi, H bar C times phi. This phi, again, is only the space part, has nothing to do with time anymore. We can now take a look at what this C is equal to. Look, this operator gives you the kinetic energy. The next term gives you the potential energy. Operating on psi, you should get the total energy times psi, right? Because kinetic plus potential equal total energy. But the total energy is equal to E. So I know that IH bar times C must equal to E, which is also equal to H bar omega. And that tells me what C is. C is negative I omega. That's what it should be equal to, negative I omega. Okay? And that makes total sense, because if you say C equals negative I omega, then we can equate this with d phi dt over phi, which is what happens here. And this equation is so simple, I'd actually go ahead and solve it directly. d phi over dt equals negative I omega times phi, move the phi over, and here is the solution right here. Phi is a function of t, is just e to the negative I omega t. There is an overall constant, which I didn't bother to write down, so I did not use an equal sign. You can easily verify that this solution solved the equation. All you have to do is differentiate that, okay? Differentiate it, don't you get negative I omega? Right? Negative I omega, and that's the negative I omega you see right here. Okay? And I said that C, it makes sense for C to be equal to negative I omega, because what you get is this time dependency, and it agrees with the expression for the wave in free particle case. For free particle case, don't we have this e to the I kx minus omega t? So the time dependent part indeed is e to the negative I omega t, which is right here. Now since omega equals e over h bar, I can always rewrite this as e to the negative I e t over h bar, e being the constant energy in this process. So therefore, if u is not a function of time, then I can simplify the Schrödinger's equation. I can solve the time-dependent part of the Schrödinger's equation by separating the wave function into two parts. Here is the time-dependent part, which I already solved, and here is the space part, which is what I still need to solve. And as far as the space part is concerned, what is the equation for the space part? You just equate this with C, which is negative I omega, and omega is e over h bar, and then you just get this. Okay, this is what's called the stationary state Schrödinger's equation. It is a special case of Schrödinger's equation given the condition that the potential U is not a function of time, so we basically have conservation of energy. As time progresses, this particle, described by this wave, the energy of this particle never changes. It's a constant value. And how does that equation simplify compared with the original equation? Well, the original equation, as you see, has both time derivative and space derivative. But I have now replaced the time part with a constant, E, because that makes sense. The energy is conserved in this case, right? So it's just a constant. And instead of IH bar partial t, which is a differential operator which gave us the energy, we don't have to use a differential operator anymore, because after all, it's just a constant. So essentially, you can understand this with the notion of conservation of energy, kinetic energy plus potential energy equal to the total energy. And in almost all cases that follow, we are going to only focus our attention on the stationary state solution. In other words, we usually do not discuss the case when the potential is a function of time, so we do not have to solve the full Schrödinger's equation, we just solve the stationary state case. There is no derivative on time anymore.